So it's an honour having Richard Blewett with us today, with an impressive 31 years of Geoscience Australia, receiving the Public Service Medal this year, and all-round awesome human. I'm so grateful to have him on today to chat about Archaean Orogenic Gold, a mineral systems approach for predictive targeting of the big ones. So it's going to be an epic session. Please use the chat. You'll have the chance to jump off mute and have some discussions at the end of the presentation. And yeah, I hope you all have some fun. So thank you so much, Richard. It's awesome having you.
Look, thanks, Jess, and congratulations on hosting GeoHug. It's a great Friday institution now, and lots of familiar faces. So thank you very much for being such a wonderful host for all of us, and providing us this forum to chat about geology and minerals. So look, thanks very much, everybody, for joining us. I sort of got into the Archaean. It's a most fascinating era of geological time. Back in the mid-90s, I was running the North Pilbara mapping project for Geoscience Australia, working with the GSWA. So that's when I first sort of stepped my toes into the Archaean rocks. Absolutely wonderful scenery and absolutely wonderful rocks, and amazing people who've been working in that area. So it was a very steep learning curve starting off into the Pilbara. After the Pilbara, I then moved into the Yilgarn and spent the next decade, so through the early 2000s, I worked up to about 2010 to 12 in the Yilgarn, and a range of projects, MIRA projects, and a PMD CRC project, which the results of which I want to be talking about today. So although what I'll be talking about is nearly more than a decade old, I think it's still relevant. There's quite a few publications coming through and sort of findings coming through in the literature more recently. I guess what I want to show is that a lot of this was understood more than a decade ago. What I want to show is how we knew that, how we were able to bring that understanding to be predictive. So lots of people to thank. This is obviously me presenting, but it's on behalf of a massive team. I had the great fortune of working in a CRC, Predictive Minerals Discovery CRC. What they are, for those who aren't aware, is a collaboration between government, industry, and academia to work on major problems. And this one was for Predictive Mineral Discovery CRC. And I had the fortune of leading this wonderful team here. So I want to acknowledge all of those people. I also really want to acknowledge some key industry mentors. I think one of the benefits of a CRC, particularly for someone coming from government and academia to be honest, is working very closely with industry on their problems and meeting their needs. And people like Greg Hall, John Ronsky, Justin Osborne, and Mike Nugas were absolutely fantastic to work with. And I learned so much from them, and I hope they learned stuff from us too. And I think they did. So it's very much a team effort. So in terms of an outline, I'll give a brief introduction, but then I'm going to go through terrain to district targeting, and then terrain to regional targeting, and then district targeting. So this talk really is the first half of a longer talk, which takes it down even into the ore deposit targeting. But I'll just talk about the first two sort of steps. This is a pretty old diagram, one that John Ronsky developed back in the 2000s. And what he's looking at is a mineral deposit sits up here at the top of an apex of energy and mass flux. So these things are happening from the global scale and are getting focused right up to the site of your ore deposit. So these are focal points. Mineral deposits themselves are focal points of these large energy and mass flux systems. What's good about this sort of thinking is that generally the larger and more energetic systems equal bigger deposits. So we can see the sitting behind it, the big footprints about that. What's good about that is these larger systems have larger signals. So if we're out there in that big broad regional area and mapping those broader footprint signals, we've got a greater chance of being in the right place. One of the problems, I guess, is that even though we can recognize this system and the elements of the system, the actual precise genetic links with mineralization are often unclear. So there's still a lot of work to be done. I love reading economic geology papers like everybody, but often I'm left wondering when I read those papers, I haven't really understood why the deposit is actually where it is. And what we tried to do in the PMD CRC was not only understand why the deposits were where they are, but where was the next one. And I guess for an industry, exploration industry, that's the important question to answer. So back in the 2000s, the mineral systems concept that we were sort of working with, and there are various versions of it, was based around the 5 questions. Now, it's not something that the team at GA use particularly now, but it was what we were using then. It's evolved since then. And there's been evolution in quite a lot of the thoughts of what I'm going to show, but I still think it's worth running through this. It's quite a nice framing. It actually had a precursor from the petroleum area as well. And it was, this I think was Bruce Hobbs's inspiration. And so it's the idea of that a mineral system has these 5 components, or five questions that you want to ask. What is the geodynamics of that system? So that's the geology, the stratigraphy, the structural history, the metallogenesis, and the metamorphic history. What is the architecture? So that's the faults, the folds, the whole sort of skeleton that sort of makes up that that hosts that geodynamic framework. And it happens from the sort of the nanoscale right to the whole sort of lithospheric scale. What are the sources of the fluids and any reservoirs? What are the drivers of those fluids, and through what pathways? What bit of the architecture is important for mineralization? How are the metals transported, and what is the depositional mechanism? So those are the sort of the questions that we were trying to answer for orogenic gold, and particularly in the Yilgarn, which is where we were based. And our approach to this was to integrate through time and space, through a whole bunch of synthesis. When we look at least in the eastern Yilgarn, and again, the numbers would have come up, but the patterns won't have changed in terms of the N there. At the bottom of the diagram down here, 3.1 billion years up to 2.6 billion years. So pretty much through the Archaean there. And you can see the Eastern Goldfields has a bit of an early history, and then it just goes crazy from about 2750 to 2760 or 70, and then, 2600, and then shuts off. If I compare that with the Pilbara, it's about 500 million years as opposed to around 100 million years. So there's something telling you about the energy of that. So what we did is synthesize out, working with, again, the great body of work that had been done before and were happening in projects at the same time. Work of Mark Barley and others in terms of understanding the stratigraphy of the Eastern Goldfields. And what's interesting is when you compare the stratigraphic evolution, it's very similar to what you see in all Archaean granite greenstone belts. You'd recognize these patterns, the mafic, ultramafics, through the intermediate volcanics, through to these lake basins. Similarly, the magmatic evolution, the granites, so these are granite greenstone belts we're talking about, they have, again, a similar pattern. We have different granite types. These are high calcium granite types. These are higher pressure melting of mafic precursor rocks. They make up the bulk of the sort of the volume of the crust, at least at the crustal level we see. Then there's another type of granite, which is around 20%, which are what we call the low calcium. They're the higher crust. And then we have these very interesting ones, which are low proportion melts. These are the mafic granites, the sinucatoids, the cyanites, and the lamprifiers, and things like that. They come in there. So there's these particular time windows of when things are happening. Then we have the amazing, so this is work by Dave Champion and Kevin Cassidy, and a whole series of Amara projects, fantastic work for the Yilgarn. Some brilliant work by Ben Goscombe, mapping out, and I think it's the best piece of metamorphic work of any Archaean terrain, was what Ben did. And we can see a very complicated metamorphic evolution, which I'll speak to later through the talk. And then this is sort of, I suppose, where I put most of my time and effort into, was working with Coral Chanota, mapping the structural history of the Eastern Goldfields. And what we see is the area is dominated by extension with some contractional events interspersed with it, and then a series of contractional events and pressional and transtensional events, and final sort of relaxation. And then we see a gold history starting around about here, where we get one of these changes, and going through to around about here. About four gold events punctuated through that period of time. The importance of doing this analysis is recognizing that this is a system, and a change in one of these elements changes the whole lot. And this is, again, a pattern that we see again and again in my literature review and my studies of other Archaean areas. We see these same sort of patterns. The other bit of synthesis we did was not only that sort of geodynamics, was actually, well, what's the sort of the architecture, the space. We're very fortunate having GA and GSWA, at least over here in WA part, acquiring fantastic geophysical data sets, which allowed one to develop really good geological maps. The underpinning of a mineral systems approach and an understanding, well, any geology is obviously a geological map. So we're able to construct these sorts of maps. Also take them into the third dimension. We had the benefits of some magnificent geophysical data sets, seismic, magnetotellurics, and passive seismics. And here we see a shot. It's the whole Norseman Walloona belt. So this is about 1,000 kilometers. It's an oblique view, 1,000 kilometer long, the big architectural framework for the Eastern Goldfields, down to 150 kilometers. We can zoom up in towards the upper crust and start to image the shape of those greenstone belts. They're like egg cartons. And again, that proved to be important in understanding the prospectivity of the region and some of the geological controls. So this is a density image of the greenstone belts, so through inversion. We can build 3D models of particular regions. So this is around the Kalgoorlie area or around particular camps. This is what we did. So we successively built a whole series of models from the whole terrain down through to individual deposits. And there's Sunrise Dam, and trying to understand the distribution of gold along particular shear zones within that. So this body of work integrated across all those scales, from the whole lithosphere right through to just cleverly put ore onto the synchrotron to look at how the deportment of elements was occurring. This is a diagram from Cam McQuaig and others, and I really quite like it. You may have seen it. So really what it is an effectiveness diagram. So the low effectiveness to high, and here's scale along the x-axis, so some broad regional, so the big sort of terrains down to within the prospect, the deposit and the prospect. And what we see is the effectiveness of trying to predict where to be. So you can be pretty certain that at 1,000 Ks by 1,000 Ks, this is a favorable area. As you come to the right, your predictions drop off in terms of your ability to be precise, particularly as your data tend to drop off in terms of quality or resolution, shall we say. What you do, though, as you come to the right, you actually reduce your flexibility, because you've already chosen an area where you're not going to be. And so it's really important that you choose carefully at these higher scales before you actually start spending a lot of money in your prospect area. The other dimension to this graph is detection. So you can, if you're in a really good area, you can spend money wisely, because it's expensive, often these detection technologies, and you want to limit that search space to as small an area as possible. What we find, of course, is the big broad regional areas, you're dealing often with the pre-competitive data that's delivered by governments, and the data-rich areas, often the brownfields areas. And we have this really difficult area in the middle, which is sort of where is the next camp? And that's a lot of the focus of what I'll be talking about, is how you can go from those data-poor areas, relatively data-poor areas, more closely into those more data-rich areas. And it's by integrating across these scales that we were able to do that. So as I said, this talk, I'm going to talk about the first two scales. So the first one is recognizing 1,000 by 1,000 kilometer area. The second one is within that 1,000 kilometer by 1,000 kilometer area, where do you want to have about 100,000 sheep, a 60 by 60 area. And I won't talk about those tighter targeting, because these all have to nest in through there. And again, thanks very much to Greg Hall. He really drove this in terms of our thinking, and it drove my thinking then on. And how I approached running the mineral systems branch at Geoscience Australia was a lot of that was inspired by this work and people like Greg. So where we're talking about is this big broad regional area. We think we can be pretty effective at predicting where we want to be. So these are sort of questions around global area selection or Australia in general, where we're undercover. Now, at the time, I think we felt that we needed a bit more comparison synthesis. We were doing some of these synthesis of other Archaean terrains so we could really understand the context of the Yilgarn. And the sort of question you're asking is, would I want to be in the Yilgarn compared to the Pilbara? It's interesting how the Pilbara has turned up to be quite hot property, and particularly in areas that around the Mallina Basin and so on. And as I go through this talk, you'll see why. What you're looking at this scale is presence or absence, so of proxies of a process, as opposed to exactly where they are. You just want to know that they're somewhere in that 1,000 by 1,000 area. So as I said, it's based on sort of synthesis of what's been done. And we did this for some other areas. We looked at even into a Proterozoic system, the Birimian, and even into a Paleozoic, the Massif Central in France. What was quite interesting is, again, this sort of systems change where you get a change in one of those elements, you get a change in all of them. And where a lot of those changes, particularly in the structural and the metamorphic history, we see gold deposited. That seemed to be a pattern that we were seeing. So the sort of processes we were after to find our 100,000 by 1,000 is a vigorous tectonic system. And the proxies for that process might be elongate orogenic belts, such as we see in the Eastern Goldfields, as opposed to the more ovoid dome and basin. And as I said about the Pilbara, the Malina Basin is an elongate part of that system, which is interesting, is where a lot of that new interest is being applied. Subduction accretion, you'd see that in the geochemistry. Tectonic mode switching through synthesis of structural histories. If you believe subduction occurred back in the Archaean, and those many don't, or delamination processes, you'd be looking for those sorts of vigorous parts of the system in the rock record. Another part of the proxy to the process would be core complexes, or these lake basins, where you see mid-crustal rocks being brought up to the surface and deposited into in the hanging walls in these lake basins. And here's Scotty Creek Formation. These are good examples of that. The timing of events. So when we look at crustal growth, it's from 3 billion to today. And we see when gold was most endowed, and it appears to be in this particular period, this Neo-Archaean period. And as we saw earlier on in the slides, we're particularly vigorous time in the Eastern Goldfields, or in the Yilgarn was at this time. So it's a good place to be. We want to see evidence of large-scale heating and fluid systems. We can see that in the metamorphic patterns. We can also see it in the widespread preservation of low calcium granites or A-type granites. These are the green guys all in here, and they're in the footwalls of those big extensional shear zones. They've come up from the mid to upper crust and exposed at that level now. They're in the centers of the domes, and they're underneath all these greenstone belts. We want to see also evidence of metasomatism in the mantle, or some sort of rejuvenation. So thinning of the lithospheric, we can see that in the signals. Relatively juvenile, that's a pattern we see. This is amazing, inspiring work from Dave Champion and Kevin Cassidy. First neodymium map showing the relationship between gold, nickel, base metals, and so on, and crustal age. So these more slightly intermediate areas, or relatively juvenile, as opposed to the more evolved crust that we see over in the western part of the Yilgarn. Want to see evidence of subduction and/or mantle plumes, greenstone sequences. These mantle magmas, synucleatoids, we've been hearing a lot about that lately. Dave Champion did a lot of work with his Amara project, identifying where those are in time and space. These mafic type granites, and they prove to be really important. But you want to see those in your system. You want to see pathways to the mantles, and these can be these alkalic intrusions, these cyanites, kimberlites, and amplifiers, etc. Any evidence of sutures, big crustal cracks, so big gravity worms, for instance, and even the dikes. This has sort of been well known. Western mining understood that. You know, these big dikes that sweep through those dike swarms. They're using pathways that were already probably evident or available to the mineral systems even hundreds of millions years earlier. And we want to see preservation. So it's again about crustal level, the widespread low calcium granites and green schist grade metamorphism. And it also helps that you have a convergence of favourable processes, i.e. evidence of mineralisation already. And we know that from the Eastern Goldfields. This isn't going to work so well in a completely undercovered or greenfields area, but it tells us, you know, the Eastern Yilgarn is a good place to be. And so that's our 1,000 by 1,000 kilometre target, and it was somewhat sort of contrived because we were working there anyway, but it was good to try and understand why it was an important place to be, at least at that scale, and what the sort of elements of the system that make the Eastern Goldfields good that you could then apply somewhere else. So the next scale we want to look down is about 60 by 60, which is a box about that size within that big area. So where do you want to be in that area? It's still a bloody big area. So what we did is a whole bunch of mineral systems targeting that ended up with this map. And we were aiming to make a map of blobs about that sort of size, and we ended up making it with that sort of fidelity, which I think is quite remarkable that what we were able to achieve. So I'll walk through how we did that. So the sort of scale we're looking at is this really difficult scale where you're going from big regional data, trying to identify that next camp. And I think we got it even almost close to that crossover point, that really difficult spot. So we're not looking for just the evidence or absence of those processes. We actually want to map where they are. The processes that we want to look for are gold-enriched crust, connectivity to the metasomatized mantle. So there's similar proxies that processes that we're looking for in the scale up, but we want to know exactly where they are. The architecture, the hydrothermal systems, and some of the cover and dispersal processes. So again, we had remarkable geophysical data sets that allowed us to make these the solid geology maps. We drew serial cross sections and we built 3D models of all of that. So these are the underpinning sort of data sets, fundamental data sets that were seamless across the whole North Moor lunar belt that we used in the analysis. I just want to touch on weighting factors because they appear through the talk. So we assigned a weighting factor of 1, where we were not certain that the process was that critical, or we were uncertain of the significance of that process, or it had large spatial uncertainty. In contrast, if we thought that this process was absolutely essential and we had high spatial accuracy, we'd give it 3. So as we start to stack this up in a GIS, and I'll show you as the talk progresses how this happens, we're weighting the things that we're more confident about, both spatially and I guess conceptually. And weighting factor 2 is somewhere in the middle. Now, they're somewhat arbitrary, and you can play with those numbers. And the beauty of this approach is there's the data, there's the interpretation. You can assign your own weighting factor, and you can do your own additions. You could multiply the weighting factors as well, it doesn't actually change the patterns that much. So coming back to this diagram that I showed in the first couple of slides, it's a slightly different version. I'm just going to walk you through some of the geological history in 3 basic time slices. There's sort of the early prehistory, just little records of it. All goes crazy from about 2720 to about 2650 in terms of stratigraphy. Granites carry on to about 2600, and then that's it, off. So as I said, there's a switch. When there's a change in one of these elements, there's a change in all of them. So this is why it's a system and how you can map it, and why it's important to map all of this and to integrate. So we use that mineral systems understanding around these 3 geodynamic episodes that we sort of loosely categorize as pre-main ore, this main lithospheric extension, and then some later inversion, again, major gold events. So it gave us sort of 3 sort of prospectivity periods. And then we mapped in some chemistry. Now, we didn't really have a good timing of the chemistry, and I guess it was a weakness of the work. And if I was doing it again, it was something I'd try and do. So I had to try and, in time, as well as space, map fluid history into that sort of more tectonic elements that we've got here. So in terms of the early history, so the Eastern Goldfields sitting over here was developed on thinned, sort of evolved what we call the Uani. It was an old sort of craton on crust. We see little pockets of outcrop granites and greenstone belts preserved. And here they are through here, bits and pieces. Granites, not much volumetrically either. And we see in terms of the younger granites, some inheritance that's going back. So we know that there's older crust underneath, probably a bit thinned under the Canalpi terrain. And that's largely what's reflected in those Sumerian patterns, which is the next slide. So here's that more evolved crust. We've got this big extensional system that was rifted, and we have a more juvenile part here, a bit more juvenile part. Now, these maps have been improved. Just WA have done a whole lot more work, but fundamentally the patterns are the same. One thing I found really interesting in this, there's enough data to show how these embayment, these salients and promontories of the Sumerian Indian patterns appear to be quite important. They're again telling us they're these sort of cross arc, it's not an arc, but these sort of cross structure linkages and accommodation zones. And these are important sort of broad structures that host mineralization. So it's even evident in the Sumerian Indian data. So we wanted to be in these more intermediate age crust. We're not so sure about the weighting factors here. So we're giving it a weighting factor of 3 for the intermediate and the more juvenile giving it 2. It's more of an empirical thing. So we end up with a map looking like this. What I'm going to do is just go through showing you these maps, and we're just going to stack them and add them and color them according to how many times that proxy to that process sort of lines up with the same space. As we come through into around 2720, really the initiation of the main greenstone belts. This was the model we had then. Now, I'm not sure that I'd run with a model like this. We've had some talks from Lyle Harris and others around perhaps alternative tectonic models. I think I agree with them, but let's just go with this for the time being. I won't spend a long time on these. You can ask me for a copy of the presentation, and you might want to go through some of the details that's happening in the text in these. There's a lot of cartoons, but perhaps I wouldn't stick this fella coming in from the east now. I might do another interpretation. Anyway, so that's sort of what's happening. We've got it sort of in some sort of back arc area there, Kalgoorlie, the stratigraphy happening in there. Various metamorphic things happening. We've got some quite high pressure rocks being formed there, which we later see come to the surface in the main extensional event, which we'll come to. Then coming into the second stage, we get more intermediate volcanics. This is when the granites really start kicking off volumetrically. So these have to come off a mafic source. So it's not directly out of the mantle. The mantle's already melted to make basalt, and then you melt that and you make these high calcium granites, and they're quite deep. So there are alternative methods of doing that. And you've got to do it quite widely across a large area and a lot of volume. It's a significant sort of mass problem to do. Nevertheless, we're starting to make this sort of granite greenstone area, and we're developing a sort of a restitic sort of dense body at the bottom of the crust. So we're ending up with this sort of jelly sandwich of high heat producing granites underneath a very dense carapace and underpinned by a dense bottom. Yeah, okay. Then the world changes. We get a contraction first coming through. We fold the greenstone sequences, and we get a diachronaity of folding and some thrusting across the early greenstone belts. And this is interesting, where the maximum metamorphic fluid release happens at this period of time. And we can make gold with that. So we want to be within 400 and the 500 window, and we can map where those are. That's a wonderful work of Ben Goss. So that's those areas where we've got less than 500 degrees assemblages preserved at that time. So we combine those two maps, and we end up with a map looking something like that. So we've just added those together. So we're combining the crustal endowment and the M2 metamorphic fluid release. So we're going to move into the third geodynamic episode, and this is when gold really happens for the first time, significantly. This is the main lithospheric extension, and these are the elements that we're able to map through that. So these are these beautiful lake basins. These are the Temiskaming things in Canada, which I've had the pleasure of looking at. These are the Malina Basin in the Pilbara. I forgot the name of the slave and the cup vial, but anyway, these are the pig well graben and things like that. What we see is a tailing off of the high calcium granites, kicking in of these mafic type, these synucleatoids and the cyanites and so on. So again, volumetrically quite small, but they come in then really, not so much for the first time, but certainly in abundant volumes. Gold first starts, and we get this major extensional event. And we get some really interesting metamorphic patterns, these anti-clockwise PTT paths and a really high geothermal gradient. So this is a really important period. This is when the world changes. We think that contraction, whatever drove that, made this unstable situation that we had before drop off its bottom. So the thing that was holding it all together fell away, and we basically broke the crust. And the big extensional detachments happened. We then unroofed those granites. Those things were eroded and put in, and the results of that erosion was deposited in those lake basins. So those are the big cobble conglomerates and things like that. These are dramatic events. And we bring up high pressure rocks in the footwalls of those extensional detachments. So things from 8 kilobars of depth, and these very interesting PTT paths. We had the benefit of some early tomography there. It's when I first fell in love with passive seismic to see the applications of this. So this is again looking off to the northwest. This is sort of Australia-wide and global tomography. The next slide is going to be a visualization of an isosurface at 4.8 kilometers per second. This is of shear wave velocity. So this is this unusual looking sort of shape. It's sort of somewhat exaggerated, but what I wanted to show is that it's not a uniform body. It's got steps and blobs to it. Hence the cartoon that we saw earlier. And there it is, more of a looking straight up the barrel of it. And this is the MT. Again, where I fell in love with MT for the first time back in 2005, working with Graham Heinsohn and Indrajit Roy, seeing the role of MT and being able to use that to map these large systems. And the mineralization sits largely in this corridor, this very conductive bit up here. Anyway, I digress. So here's what this thing looked like again. This is sitting down at about 120 to 150 kilometers, the top of this thing, and again, some interesting shapes. Let's just project the edges of this up. Then we'll look at where those alkalic rocks are, amplifiers and things like that, and they tend to sit. So they're telling us something about those pathways deep into the mantle that I was talking about earlier. And then we look at where the gold is. So we see the Kalgoorlie area sits there. It was really interesting. So when we were presenting this back in 2007, when we first had all this, we're sort of saying that this is a really cool area out in here. And it's, of course, that's out where Grue areas. Other favorable areas from that. So that's the trace of those things. We're putting a weighting factor of 1. It's uncertain in terms of the connection to the process, as well as the resolution of those data and the accuracy of those. So we put a pretty wide buffer, but we're also not putting a high emphasis on it. One thing we do put a high emphasis on, though, is this connection with metasomatized mantle or enriched mantle, weighting factor 3, and spatially we know where they are. You can go kick them. So these are the mafic granites, the sinukitoids, the cyanites, kimberlites, amplifiers, etc. So they're telling us about that. So we want those. They're cool things. So combining that together, we have the proxy layer. Right. The next bit is, as we rip the crust apart, that happens across these big extensional detachments. Now we can map out those. They are the boundary between what we call an upper plate and the lower plate. The lower plate is defined by these high pressure metamorphic rocks, which you see in the red, and the anti-clockwise PTT paths in the lake basins in the upper plate, as well as the location of the lake basins themselves. So we can map out those detachments, and they're commonly many of the big shear zones that get reactivated later. But that's where you have massive dislocation and juxtaposition of crustal levels is across those zones. And there's an interesting sort of east-west trending, northeast trending sort of accommodation zones to that extension. Now, why is extension important? Heather Sheldon did some great work. So you've got these basins with fluids in them. Under extension, not only can you break the crust, but you can draw fluids down. So here's an opportunity to mix fluids of very contrasting chemistry, which can be part of the depositional process for gold. One of the great things about working in granite greenstone belts is you've got a very dense greenstone belt made up of basalts, basically, and you've got light rocks like granites. And the contrast between those we can map with gravity. So we want to look at those big detachments are going to be reflected in the gravity data. So we want to look at the gravity worms. So we continue to 45 kilometers. This is what Indrajit Roy did, and come up with a map something like that. So let's combine the big extensional detachments, the connection with the mantle, the deep pathways in the tomography, and the gravity, and we end up with that map. So now we're going to go into a period of time when the Eastern Goldfields went back under contraction. We're going to talk about domes, we're going to talk about some of the major faults, and we'll also talk about things that happened in the upper plate. So here's the period. Basically, contraction started again. We shut off sedimentation, volcanism had shut off before. We also go into this switch into what we call these low calcium granites. There's a lot of heat in the crust. We're starting to melt those at higher levels, and we're getting those big granite blooms, those big, what we call the low calcium granites, and getting a lot of gold. And we see several contractional events. I won't spend a lot of time on that. I broke compasses mapping all these things, Carol and I, fantastic. A lot of the deposits sit on the structures that are associated with these. you can map individual gold events to individual structural events. It's pretty cool. And be very predictive with it too, but that's at the next scale down. So we see, again, I won't spend long on that. That's sort of a bit of a cartoon of what's happening. A couple of contractional events, some of the main gold events, and another sort of switch. And it's starting to look like what we see now preserved in the seismic. So this is the NY1 line between Leonora going out through Laverton. Here's the Yamana shear zone. And it was really interesting, you know, back in 2001 when we acquired that, GA and GSWA acquired it, I was getting up talking about, you know, we reckon this is prospective. And of course, Gree is a long strike from this. So it's a whole new field that was, I guess, attracted. The investment was attracted on the basis of that. And that's one of the purposes of what governments do, being able to do these big data sets, and they really can change the minds. But it takes, you know, this was 2001 and it wasn't discovered to 2014. So it takes time. Okay, so what are the processes? Faults. We know faults are important in orogenic gold. Here's a map. We had a solid geology. We understood those faults in 3D, of course. These strain localization, and of course, their pathways for fluid flow. And we know we don't necessarily want to be exactly on the fault. We usually want to be on second and third order structures around it. Great work by Steve Cox and Kev Rooming and so on. Steve Micklethwaite's done a lot of work on this. So we'll put 5 kilometre buffers either side of it. We want to be sort of in proximity to these. So these are good places to be. The next data set is, I've shown you this before, but let's just look at the upper plate. So what we're looking for is lower grade rocks that are likely to going to be brittle, facilitate fluid flow. The lake basins themselves possibly could be regional aquatides, and they could be some of these threshold barriers that people like Ronsky talk about. We see these are also reservoirs for fluid that can be drawn down in extension. We also know these are the locus of the high heat flux, because we see that in the metamorphic patterns. They just go raw anti-clockwise. And so we map those out. So that's looking at the data points of the metamorphic points, the location of the lake basins, and the M1 data points, which are in the footwall, the lower plate. Domes appear to be important in this story. This is again a map from Paul Henson, but it was work done by Mike Barlow, inverting the gravity data. But it was a constrained inversion with something like 300 cross sections to make this. So we had a really good understanding of the shape of the greenstone belts. These domes, they localize strain on their flanks. They're also focused in the dome apices for some deposits as well. Now we looked because most of the analysis has been done in 2D, just for simplicity, but we had a 3D, 4D understanding of what we were trying to do. We then tried to bring this into the 2D world as a series of contours, but there are many anomalies with the inversion still. We weren't confident, so we just reduced it to a weighting factor of 1. And there's the product of that map. It looks something like that, the proxy layer. So let's combine that, the major faults, the granite domes, the upper plate, and we get a map something like that. That's sort of those, so the warmer colors, I probably should have said that in the beginning, are sort of the more preferential areas based on those elements of the system that we've been able to map. As I said, when I first introduced this slide, we were trying to look at the fluid history. What we didn't do very well was really map the fluid history through the time and space. We're able to look at it sort of, I guess, from a finite point of view, but really not look at it incrementally as we were going through the system. I think that's a body of work that could be done and should be done. But what we're able to do is there's, again, vast pre-competitive information available out there from GA and GSWA. And we were able to look at the OzChem database and look at the loss on ignition. Now, we scaled it based on the lithology because different rock groupings have different propensities for alteration and being hydrated. So what we're looking at is basically the amount of hydration in the system, but we scaled it accordingly. So we weren't comparing a serpentinite with a dry granite, for instance. The other thing about this database is it was government geoscientists tend to try and get away from alteration, try and map and get back to the primary lithology, the primary chemistry, and so we were, I guess, confident that we were getting as far away as from alteration. They weren't collecting the most spongy rocks. They were trying to get the freshest rocks possible. So despite that, And despite that, they were still getting these hydrothermal cells. The amount of alteration is so much that it's almost impossible to avoid. So we then mapped these, the largest of the hydrothermal cells. Another thing that's sort of come to the fore, and it's worked from people like Scott Halley in particular, noted the relationship between gold and these in various proxies to the process, like PEMA and auric geochemistry, magnetics, mineralogy, and isotopes. So here's PEMA. Here's the view of the Kanowna Belle shear zone, and the gold deposits just sitting off that gradient in ALOH wavelength. So this is probably telling us something about chemistry. It's also telling us about redox state. So John Walsh and Scott Halley and Janet Tunjic came up with this really cool sort of triangular diagram of basically different fluid types. You know, they recognized three main fluids in the system, and the best gold grades they noticed were somewhere between the reduced alkaline and the oxidized alkaline. And there's a whole bunch of proxies that you can use, mineralogy or isotopes, that can tell you where you are on that diagram. But basically, we want to be somewhere there. We have a lot of mineralogy. Ben Goskin looked at 12,000 thin sections to make his metamorphic map. Again, it's just like only Ben is the only person who probably could do this. And so he was there looking at taking that Walsh diagram and trying to map mineralogy based on that. So we were able to look at whether we were in these oxidized or reduced fields. So we're able to map those out and then map out the gradients, and those are the green blobs. So let's just combine those two data sets just from mineralogy that exists and the loss on ignition. I was sort of really struck by how that gets you into the main camp straight away, instead of tread on the ground. I think chemistry is an amazing data set, and I'm saying that as a structural geologist. Okay, so we've got those 4 maps that we've produced, and we can bring them together. So basically, we know we decided that we were able to add them up because we were able to see the big deposits have multiple lightning strikes more than once, and the really big deposits have these multiple events within them. We were able to map that out ourselves, and so we just simply added these maps together, and we ended up with this map. And I said we were absolutely blown away by the fidelity of it. Now, I would say the way we did it was on A0 plotting paper at 1 to 750,000 scale. So the sort of the input data sets were drawn up like that. They were digitized and then put into the GIS, and the GIS was built. So it's really pretty crude. We were only trying to get big areas. The fidelity of these was really quite amazing. Just remember, we haven't put a deposit in here yet, and I'm putting it in now. So that was the test. Now, did we find the gold? And the answer is yes, very well. Look at the main camps, Leonora, Laverton, that sort of Kalgoorlie to St Ives. We picked that up. It came roaring out without us putting those deposits in. So it's this is a knowledge-driven process, as well as a number of areas that hadn't really been attracting attention. What we've been talking about is actually reducing the search space, and how well have we done that? So this diagram is a bit to take in, is showing these sort of weighting factors up here, as well as a percentage of area and the gold. So if we read off this area here, if we don't add any buffers to this, if we just look and then try and intersect the known gold with these higher areas, next slide, then we would get 75% of the gold in, what area? 70% of the area, that's right. If we just add a 2.5K buffer to those areas, we get 90% of the gold, sorry, in 12% of the area, that's right, in 12% of the area. So that's a hell of a reduction. So it's bringing the search space down to quite a small area, and you've got 90% of the gold. And I'll show you what that looks like. So that's just adding that 2.5K buffer with a weighting factor of 15 and seeing what you find. So those bullseyes on this map are important. And if we go in and look at Norseman, remember I said this was done, the scale of compilation was 750,000 scale. So it was huge. We just, in this, it's the thickness of a pen, we missed all of Norseman in that analysis, just by a whisker. But basically, you'd think Norseman would be a good place to be based on the overall analysis. So I think it's robust. New targets with no known mineralization are there as well. So I've sort of come towards the end of the talk now. This was really about identifying the next 60 by 60. What you do from there is go into 5 by 5, and that's a talk for another day. I think this scale of what I've just shown is the most valuable scale to get right, particularly for the stretch junior. You certainly don't want to be walking away too early. So in conclusion, scale integrated targeting is, well, I think simply an integration of what's good geology with geophysics, geochemistry, chronology, the whole lot in time, space, and 3D space with a mineral systems process understanding. This moving between scales allows us to fill that sort of really difficult gap between the really data-rich areas and the data-poor areas, and working seamlessly between those. And I had the benefit of working with a large team that I don't think can be, well, is being emulated today, to be able to do that in such a focused way. It is a difficult prediction and detection. Really good thing that I learned was, and people like Greg and John, converting that knowledge. There's great academic information out there. The surveys are doing great work and continue to do so, but it's about turning that stuff into practical tools and maps that you and, or we in, I'm in industry now, can use. And I'm using these same methods right now. You need a multidisciplinary team to do it, and you need really well organized data. So there was decades of work before we were able to do that. If we'd had to start from scratch and data wrangle, we'd probably still be going. So the surveys and GA play a vital role in enabling this sort of work, and the quality of data that they deliver and allows this sort of thing to happen. It's really important what they do. So we're seeing quite a lot of this sort of stuff coming out in the literature. It seems to have been forgotten, some of this that was done in the 2000s. So I'm putting up the links to some of these reports. There's a lot more in there. So that's the Y4 report. If you go into this site, we archived it on Trove, on the National Library, because websites die if you don't keep paying for them. So I made sure that the whole CRC was put onto Trove. So you can go in and read all the old reports. There's some fantastic stuff in there, but I guess I'm focusing on the Y4 one. I also worked with in the Amara project, the Y1 one. This was the structural history. So that's this report. There's a whole sort of set of data around that too. I was conscious that this is grey literature to some people, and so put a big effort into publishing a special issue in Pre-Cambrian Research. That was in 2010. That came out. Again, that's pretty well cited. Some of those papers are pretty well cited, but I read some papers and it's almost like it's forgotten because it's 11 years ago. And the remarkable work of Ben Goscombe, his metamorphic work, I recommend you have a look at that as an exemplar of metamorphic analysis. And that's my slides and my talk, Jess. Look, I thank you for your time. Sorry it's a bit rushed. There's a lot to cover. I'm happy to take questions. I'll stop sharing my screen.
Thanks so much, Richard. That was, yeah, that was awesome.